Hello everyone. So, this is the third lecture of week 3. So, recall that we are looking at optimization algorithms. So, in the first lecture of this week we introduced the general structure of optimization algorithm, where in each iteration we will have to find the descent direction as well as the step size. And in the previous lecture we introduced two methods. One is exact line search algorithm and the second algorithm is backtracking line search algorithm. So, recalling what backtracking line search algorithm is. So, we have something called as the Armijo's condition, which is f of x k plus alpha d k minus f of x k is less than or equal to C1 alpha del f of x k transpose d k. Okay. So, the basic thing that we are expected to do is to choose the value of alpha that satisfies the Armijo's condition. Okay. Yeah, but how do we choose one? What we do is we first initialize a value of alpha and a value of rho. So, yeah, a value of C1 as well. C1 already figures out in the Armijo's condition. Okay. And until Armijo's condition is satisfied, so we actually keep reducing the value of alpha by a factor of rho. Okay. So, the question that we have now is, why does Armijo's condition work and what does Armijo's condition ensure in the first place? Okay. And so what we are actually doing is we started with a very high number and we are keeping on reducing the value of alpha. Maybe the value of alpha lies above. Okay. I mean, so let us say I started with alpha equal to 1, in the next step it is going to become less than 1, let us say 0.9. In the next step it is going to become less than 0.9, and then say it is actually 0.81, right. So, in the next step it is going to become less than 0.81, right. So, the value of alpha is just reducing. Why should I actually reduce and not increase, right. So, let us answer all of these questions one by one. Okay. So, let us first understand this condition. What is this? F of x k plus alpha d k minus f of x k is less than or equal to C1 alpha del f x k transpose d k. Note that the left hand side, right, f of x k plus alpha d k minus f of x k. So, we want to choose an alpha such that this is less than 0. Okay. So, you can recall that, is not it. So, we have this condition, you choose an alpha k such that f of x k plus alpha k d k minus f of x k is less than 0, right. So, we want the LHS to be chosen in such a way that it is negative. Okay. We also know something, we know that del f of x k transpose d k is actually negative, because d k is chosen as the descent direction, is not it. So, when you multiply with C1 which is positive and alpha which is positive, so the RHS is also less than 0. Okay. So, what does the Armijo condition say is that this quantity which you want it to be negative, right, f of x k plus alpha d k minus f of x k. Okay. So, it is not just sufficient to have it to be negative, it should be less than or equal to some particular value. Okay. So, let us expand this to understand this further. So, f of x k plus alpha d k is, so if you do the Taylor's expansion, you will have f of x k plus alpha into del f of x k transpose d k plus alpha squared by 2 del 2 f of x k d transpose and d. Okay. So, so I should actually write this as x dash k because it is not exactly x k, I mean it is between x k and x k plus alpha d k. So, that is fine. Okay. So, right. So, what do we want? So, if f of x k plus alpha d k minus f of x is less than or equal to C 1 alpha del f of x k transpose d k, which is the Armijo's condition. Okay. Then what happens? Substitute f of x k plus alpha d k minus f of x k to be this. Okay. So, then you actually get alpha squared by 2 d transpose del 2 f of x dash k d is less than or equal to C 1 minus 1 alpha del f of x k transpose d k. Okay. So, you can see that the right hand side is actually positive. Why is that? Because del f of x k transpose d k is negative and C 1 minus 1 is negative. Note that C 1 is less than 1. Okay. So, that comes here, C 1 is less than 1. So, C 1 minus 1 is less than 0 and del f x k transpose d k is less than 0. Okay. And alpha is positive. So, the right hand side is actually positive, and if f is positive definite at x dash k, right. So, I mean if f is convex, then that obviously holds, right. So, then you can actually see that yeah, d transpose del 2 f of x dash k d is positive, right. So, this is positive if f is sorry, yeah, you can say f is convex at, or strictly convex rather, I will write it that way, strictly convex at x dash k. Okay. So, and yeah, so you have a positive quantity into alpha squared by 2, okay, less than or equal to alpha into a positive quantity again. So, I can cancel one of the alphas, okay, and write this as alpha by 2 into some positive quantity, which is this, less than or equal to yeah, some other positive quantity, which is C 1 minus 1 del f of x k transpose d k. Okay. Yeah, here also I should have written d k and d k. Yeah, yeah. Okay. All right. So, what does this actually tell you? It tells you that if you choose an alpha which is less than or equal to C 1 minus 1 del f of x k transpose d k divided by d k transpose del 2 f of x dash k d k, then Armijo's condition is actually satisfied, is not it. So, if you have a value of alpha for which Armijo's condition is not satisfied, what you have to do is keep reducing the value of alpha. Okay. At some point this particular condition is actually satisfied. Okay. So, yeah, that is basically the reason why Armijo actually came up with this condition. So, this was a condition that was given by Larry Armijo, yeah, famous optimizer. So, he gave this in his paper in 1966, okay, yeah, quite some time before, about 58 years before. Okay. So, now coming back to the algorithm. So, say you start with some particular value of alpha, okay, say alpha equal to 1, you actually see that Armijo's condition is not satisfied. Okay. So, what you do is, I mean what does that mean? It means that alpha by 2 d k transpose del 2 f of x dash k d k is greater than C1 minus 1 del f of x k transpose dk, right. So, you need to choose an alpha that is lesser, right. So, what do? You shrink the value of alpha by a factor of rho, okay, and you check the condition again. You see that it is still not satisfied. What do? You shrink the value of alpha by another factor of rho. You see that it is still not satisfied. You shrink the value of alpha by another factor of rho. You keep doing that until this particular value is satisfied. Okay. So, Armijo's condition is basically there in place to prevent us from choosing very large values of alpha. Okay. So, we saw in the previous lecture that we are not supposed to choose very high values of alpha, right. So, yeah, Armijo's condition prevents from choosing arbitrarily high alpha. Okay. So, yeah, it also depends on the value of C1. So, if you choose a very low value of C1, you are being a little more conservative. Okay. So, if you choose C1 equal to 0.9, then yeah, you are saying that yeah, you are increasing the prospect of alpha a little bit higher. Okay. Yeah. So, yeah, that is just based on the value of C1. Okay. All right. Yeah, this is regarding why Armijo's condition is chosen, and this is basically the backtracking line search algorithm. We will actually look at an example. So, let us say, yeah, let us again look at the usual example to see what value of alpha you get. Okay. So, let us say we have f equal to x1 squared plus x2 squared, and x0 is 5 comma 4 and d0 is minus 1 comma 1. Okay. So, other than this, note that in the algorithm we will also have to choose rho, C1 and alpha. Okay. So, I am going to choose rho as 0.8 and C1 as 0.75, both needs to be between 0 and 1. So, that is, I mean, I am just choosing these arbitrary values, and I choose the initial value of alpha to be 0.5. Okay. So, let us check if yeah, let us actually find what the backtracking line search algorithm has to give us. Okay. So, one thing is, I mean, doing these maths by hand actually looks cumbersome already, right. So, we will take the help of Python. Okay. So, let me actually do the Python code for this particular example. Okay. So, let me first yeah, so it is better to import NumPy as immediately as possible, and I am first going to define f of x, which is x1 squared plus x2 squared. So, which is x of 0 the whole squared plus x of 1 the whole squared, and I am also going to define grad f of x. So, I am just calling it grad of x, but yeah, it is how we choose to call it. So, this is an array which is 2 into x of 0 comma 2 into x of 1. Okay. Yep. So, that is grad of x, and now let us actually write the code. Note that we have to define x. So, that is another array which is 5 comma 4 the initial value, and d is another array which is minus 1 comma 1, and I need to define the value of alpha, rho and C1. So, alpha was 0.5, rho was 0.8 and C1 is 0.75. So, recall these values, rho is 0.8, alpha C1 is 0.75 and alpha is 0.5. Okay. Fine, let us now write down the algorithm. Yeah, so I have initialized rho C1 and alpha. So, this step is done. Now, I need to write the while loop, right. So, let me do that. So, while f of x plus alpha into d minus f of x is greater than C1 into alpha into grad of x, okay, it is a dot product. So, NP dot of grad of x comma d what should I do? I should just multiply alpha into rho. Okay. But before that I mean I also want the values printed, right. So, I will print the values, print. So, I will do it without the format specifiers for now. I actually want the values of, what are the values I want? I want the values of alpha, alpha is something that keeps on changing, and these two. So, I will just copy them down. F of x plus alpha d minus f of x and C1 alpha del f of x transpose d. Okay. So, yeah, this keeps on going. So, let us check what the answer it gives us. Okay. So, here is the answer. So, initially we recall that alpha was equal to 0.5. Okay. And so, yeah, f of x plus alpha d minus f of x turns out to be minus 0.5 and C1 alpha del f of x transpose d turns out to be minus 0.75. Okay. So, minus 0.5 is greater than minus 0.75. So, Armijo's condition is not satisfied. So, thus what you do, you shrink the value of alpha by a factor of 0.9. Okay. So, you get 0.5 into 0.8. So, 0.5 into 0.8 is 0.4. Okay. And yeah, so you here f of x plus alpha d minus f of x turns out to be minus 0.48 and this is minus 0.6. Again Armijo's condition is not satisfied. Now, you shrink it to 0.32 and yeah, the left hand side of the inequality is minus 0.4352, right hand side is minus 0.48, again the condition is not satisfied. Then you again shrink it to 0.256 and the left hand side is some 0.38029 and the right hand side is minus 0.384. So, here the Armijo's condition is satisfied. So, we stop at alpha equal to 0.256. So, let me, I mean, yeah, so this is possibly not very conducive for you to understand. Let me possibly put it in the form of a table here. Okay. So, the values of alpha, here it is f of xk plus alpha dk minus f of xk and here it is C1 alpha del f of xk transpose dk. Okay. So, if you recall, this is 0.5 minus 0.5 minus 0.75, this was 0.4 minus 0.48 and this is minus 0.6 and then you have 0.32, here it was minus 0.4352 and minus 0.48 and it was 0.256 at the end. Here it was 3809 and this was 3840. Okay. So, yeah, initially when you had alpha equal to 0.5, the Armijo's condition was not satisfied because the left hand side is minus 0.5 and the right hand side is minus 0.75. So, minus 0.5 is greater than minus 0.75, right, it is not less than or equal to. So, what Armijo's condition says is that alpha equal to 0.5 is a little higher, right, you are possibly choosing high value of alpha, right, and when you shrink it to 0.4 it is still I mean the condition is not satisfied because it is minus 0.48 and minus 0.6. So, it is still high is what the Armijo's condition says. You again shrink it to 0.32, again it is high, you again shrink it to 0.256 and at this point you can see that Armijo's condition says Armijo's condition is satisfied and you are very sure that yeah, the value of alpha is not so high, right. So, yeah, this is basically how the algorithm functions. So, you initialize the values of the shrinking factor rho and C1 which is a part of the Armijo's condition, right, and the initial value of alpha, okay, and after this you keep shrinking the value of alpha until the Armijo's condition is satisfied. So, if it is satisfied in the first place you can stop it there, or if it is not satisfied you keep shrinking the value of, okay. So, you have to note one thing, we took the same example f equal to x1 squared plus x2 squared, x naught equal to 5 comma 4 and d0 equal to minus 1 comma 1 in the exact line search as well, and what was the alpha that we got? We actually got 0.5. So, you can just refer the previous slide, yeah, here it is. So, you have f equal to x1 squared plus x2 squared, x naught is 5 comma 4 and d naught is minus 1 comma 1, but what did I get? I got alpha equal to half, but what am I getting here? I am actually getting alpha equal to 0.256, right. So, I mean that is a very different value, is not it. So, what this tells us is that backtracking line search may not give us the exact value of alpha which minimizes f of x k plus alpha d k minus f of x k, okay. So, yeah, it could happen that I mean we are actually choosing an inexact value of alpha. So, I mean these are actually called as inexact line search algorithms. So, not just this, any other line search algorithm other than exact line search algorithm is inexact line search algorithm, okay, because it does not it need not give the value of alpha that is given by the exact line search algorithm, but I mean in many of the cases, I mean if you I mean do not choose a very high value of alpha, right. So, I mean the Armijo's condition actually prevents us from doing so, because of which, yeah, we may take a few more steps, but we are able to converge to the right answer, and note that the advantage of backtracking line search is that you can use it for any optimization problem. You need not I mean you need not check for the tractability and so on. So, we just saw that for exact line search, I mean we need not I mean we may actually have tractability issues, right. Analytical tractability was one of the issues that we were having an issue over, right. Such an issue will never happen in backtracking line search. You can use it for any differentiable function f, okay. So, that is why this is more popularly used. For simple functions you can use exact line search, but even if it is slightly more complicated you actually come to backtracking line search, okay. So, I would like to introduce you to two more conditions, okay. Yeah, Armijo's condition is what prevents us from choosing arbitrarily high values of alpha, but I mean we do run the risk of choosing arbitrarily low value of alpha, right. I mean, so that is Armijo's condition actually does not prevent us from doing so, okay. So, I mean the two conditions that I am going to introduce now will actually prevent you from choosing arbitrarily low values of alpha, okay. So, what are those conditions? One is called as the Goldstein's condition, So, Goldstein condition gives a very similar flavor. It is f of x k plus alpha d k minus f of x k is greater than or equal to C 2 alpha del f of x k transpose d k for some C 2 in the open interval 0 comma C 1. So, yeah, you can see that the condition for Armijo and Goldstein is I mean it is just. So, instead of the left hand side being less than or equal to C 1 into something, it is greater than or equal to C 2 into the same quantity, okay, and C 2 needs to be chosen, C 2 needs to be positive and it must be chosen to be strictly less than C 1. Okay. So, that is Goldstein's condition, okay. And you also have this Wolff's condition. So, here suppose you define phi f alpha equals f of x k plus alpha d k, okay. So, the condition is yeah, the phi dash of alpha k is greater than or equal to C 2 into phi dash of 0 for some C 2 in open 0 comma C 1, okay. So, yeah, these two conditions are similar, I mean it is not exactly the same, but they are quite similar, you can say. I mean if you want to understand why it is, you can just write this condition that the phi dash of alpha is dk transpose del f of x k plus alpha dk, right. So, therefore, phi dash of alpha k greater than or equal to C 2 phi dash of 0 just implies del f of x k plus alpha dk transpose, sorry, alpha k dk transpose dk is greater than or equal to C 2 into yeah, del f of x k transpose dk, okay. So, yeah, the right hand side is similar to what you had here, okay. So, the left hand side is slightly different, I mean, but you can see that it is f of x k plus alpha d k minus f of x k by alpha, okay. So, I mean that looks like the condition for differentiability, right. So, instead you have something which is similar to what you would have for a derivative, right. Yeah. So, of course, it is not exactly the same, do not mistake that they are exactly the same, but the conditions are very similar, that is what I am trying to say, okay. So, suppose you want to prevent backtracking line search to choose from choosing arbitrarily low values of alpha, you can actually I mean impose either Goldstein's condition or Wolff's condition, okay. So, I will write that down as well, Goldstein's and Wolff's conditions prevent us from choosing arbitrarily low alpha. Okay. So, but nevertheless, in many of the circumstances, I would like to tell you that backtracking line search works without these conditions, works fine without these conditions. Why is that? Because if you see how we actually write down the backtracking line search, we start from pretty high alpha, say 1 or half or something, right, and we reduce it slowly, right. So, yeah, if 1 does not work, we do not immediately jump to, let us say 0.0001 or something of that sort, we reduce it slowly, right. So, usually, I mean it does not happen that we end up with very low values of alpha. We might end up, if you choose rho to be very low, right, say if you choose rho to be 0.1 or 0.05 or something of that sort, yeah, then such things may happen, but yeah, we usually choose rho to be greater than or equal to 0.5, okay, in practice, okay. So, thus Goldstein's or Wolff's conditions are in practice not needed, but I mean I still wanted to let you know. And one issue that might occur is that when alpha, I mean if you choose, let us say alpha equal to 1 or half, for example, for the particular problem that itself could be very low, okay. So, you can actually check if the initial value itself is arbitrarily low or not, okay. So, that possibly can be checked from Goldstein's or Wolff's conditions. But at least for this course we will be taking up examples where Armijo's conditions are actually sufficient, okay. So, yeah, we will end this lecture here. This is regarding the line search algorithms. In the next lecture we will actually look at algorithms that choose the descent directions. Thank you.